Recording. Okay, so I'm going to start off with I have some short slides where I'm just going to review some basics, and then after I have a practice exam and where we'll go over some problems. We're not going to do the whole thing, but we'll do most of it, and then we will do some. I have some other questions that I was asked to solve, so I'll get started with our slides. Share the screen. All right. See that? Awesome. So first of all, let's start with the fetch, decode, execute cycle of the basic computer, because now for this to work, I'm going to mostly assume that we have the basics of digital systems down, so binary logic and all that. We're going to get right into the fetch, decode, execute cycle. So SC is your system counter. So that starts at 0, and this is like a train. It's just always counting up, and then when it reaches the end of a cycle, it will reset to 0, and you'll go back here. So as we can see here, we start at SC equals 0, and then when SC equals 0, that's T0. We have the program counter, which holds the next address to be executed. That will be loaded into the address register. Then oops, why is it doing this slow? Okay, there we go. Now we will go to that address in memory, take the instruction from it, load it into IR, increment the program counter, decode that instruction, and then load that address portion of the instruction into the address register, check into the indirect instruction, and then from here we can branch. And this might not have been the best place to start. We'll come back to this as we keep going. This is just a chart where it shows what happens for each instruction. And then, you know what? I think we'll just come back to this as we go along. So first things first, I was asked to solve this question, which is the ALU question. Just gonna hide this. All right, so I am going to turn off my camera now just because I'm gonna flip my laptop over to use it as a tablet. That's okay, nothing too interesting is gonna be happening on my camera anyways. Okay, let's do this. Got someone in chat. We had this one on the quiz, yeah. So I was asked to solve this one by some students, so I'm just going to go ahead and do this. So it's important to realize that when you get a question like this, you see, it looks like you have 8 instructions, right? But really, you only have 4. When you have this type. If you have, now this isn't the case for all of them, but that's what's happening here. And I'll just go into more details on that in a second. So if you look here, every second instruction, so it's like A plus B, the one above that is just that instruction plus 1, right? A minus 2. And then the one above it is minus 1. So that's just plus 1. So what's really happening is when X is equal to 0, we add 1. And if we look here, to add 1, this is like on a full adder when you would turn on that complement bit. What would happen is you actually feed that into the carry in of the first full adder. So we can tell right away, I'm just gonna make my pen thinner, that for this one, we're going to feed X into the carry in of our accumulator. And we know it's just X because if we look here, we have the NOT gate. So when X is 0, we want to add 1. So 0 NOT would be 1, right? And then 1 NOT would be 0. So next up, we can just start looking at what's going on with variable A. So first off, it's important to note that this is a n-bit adder, so it can be any number of bits. In this case, we are only concerned about the 0th bit and the first bit. So if this is a 4-bit adder, this is just a random number. These would be the 0th bits, and these would be the first bits, right? So, and also if we look at the A values here, they're always the same. So we don't have to put A through a multiplexer to like we're doing with B here because we have a multiplexer. A is always the same no matter what operation we're doing. So A can go right in the full adder. So if we look here, there is one input into the full adder where it doesn't go through any additional logic. So that will be our our A input. Now you can't just say like A and A, because what does that mean? You can't feed A, if in this case A is a 4-bit number, you can't feed 4 bits into one input. If we look here, we see this is the first bit of the result, and this is the 0th bit. So for the 0th bit, we want to take the 0th bit of A. So that'll be A0, and that'll be A1 respectively. All right. Cool. So I'll have the chat here just to make sure. Everyone following along so far? All right. So next up, we've done A. Let's look at B then. So the first one. For the first, oh yeah, let's do our control bits here. So we have Z and Y, and what that does, what these Z, if we look in each of these sections that I've divvied up in terms of like what operation is happening, you see here that it's the same for each section. So for this section, Z is 0, Y is 0. For this section, Z is 0, Y is 1, so on and so forth, right? So we want to be able to, and what happens is for each of these, the value of B changes, or the second operand changes. So really what this means is we're choosing the input for the second operand based on Z and Y. Y is X in box 16. So that's what I went over earlier. If we look here, you see that you have X as a control bit. And whenever X is 0, 1 gets added to the entire operation, right? X is 0, 1 gets added. X is 0. Hi there. 1 gets added. And actually, this looks a bit strange here, but I'll go over in fact, you know what, let's just do that now as to how I know that 1 is actually being added here, right? So A minus B minus 1. If we want to write this in a way that can be represented through that can be done with the computer, the basic computer, we have to turn that B into 2's complement. So that's going to become A plus B complement plus 1 minus 1, right? So that's just going to turn into A plus B complement, right? So A minus B minus 1 will be, sorry, so I'm just going to give people one moment just to settle in here. All right, so let's just go back over this here. A minus B minus 1. So A minus B minus 1 would be equal to A plus B complement plus 1 minus 1, right? Because we know that minus B expands to B complement plus 1. So that makes sense. So that means we can just simplify this to A plus B complement, right? And we know that when we established earlier that when X is 0, we add 1. And when X is 1, we don't add 1. So if we look here, we just proved that A minus B minus 1 is simply A equal to A plus B complement. And then if we want to do actually A minus B, that equals to A plus B complement plus 1. So really what we can just say is to go from A minus B minus 1 to A minus B, we just turn X to 0, which adds 1 to the whole result. Does that make sense? I know it's a bit strange. It's a bit strange to wrap your head around. I'm just reading the chat here. If anyone has any more questions, just type them in. All right, then. So I'm going to assume we understand now. So now that we just proved that a minus b is just 1 plus a minus b minus 1, which also just makes sense logically, but how we can implement this with this ALU first of all is, oh yeah, and let's do our select bits. Oh wow, we're having a lot of people. Awesome. Are there? How's everyone doing? Good.
We just started the and everyone's just spending their watching.
Wow, people. This is awesome. Oh boy. All right, so more people are just arriving. I'm gonna give them 1 minute. Hey, come in, have a seat.
Yeah, you can watch the first part. Oh, somebody.
Got it. Okay, so let's keep going. So also we want to be able to choose what input we're taking from the multiplexer. So to do that, we look here. Z is like select 1 and Y will be select 0. So we go down here, we see we have a select 1, select 0, and we need to also do the same thing for this multiplexer down here. Z, Y. Can everyone who just joined mute their mic, please? We're getting some input noise. All right, thank you. So now that we have our select bits going, we can now start choosing between our inputs for the second operand. So let's start with the first one. We just have B. That's pretty easy. So remember, we can't just say, this is just another random number. We can't just say B. We have to specify the bit of B. So here, we're just taking B without any modifications. So for the first bit, we want to take B1. And for the 0th bit, we want to take B0. And remember, I'm putting it in this box because this is when the select is 0, 0. So that'll be the 0th input onto the mux. All right. Now, next one, A minus 1 and A minus 2. So remember, the top operation is just the bottom one plus 1, and that's implemented when x is 0. So when x is 0, so 0 naught becomes 1, and then it gets added into the full ladder. So it adds 1 when x is 0. So minus, for this one, this is a constant. So we're just going to take the value 2 in binary, 0, 0, 1, 0. We're going to take its 2's complement. So that's 1, 1, 0, 1 plus 1, 1, 1, 1, 0, right? Makes sense? So now we're going to take the first bits and the 0th bits and feed that in. So into the first bit, we see that that's the first bit here, and that's the 0th bit. So first bit gets a 1, second bit gets a 0. All right. Next, we can do this here. So this is what I went over just a minute ago. So we see here A minus B minus 1. I'll just prove that one more time just for the new people that showed up. So first off, minus B will be expanded to B complement plus 1. So A minus B minus 1 is equal to A plus B complement plus 1 minus 1, which will simply simplify to A plus B complement. Okay. So, oh yeah, and then A minus B. So remember, we add 1 to A minus B expands to A plus B complement plus 1. Now remember that when x is 0, we add 1. So really, we're just saying for the first one, we have A plus B complement plus 1. And this happens because x equals 0. And now the next one, we thought boxes 5 and 13 would be complement. Boxes 5 and 13, they are complement already, because remember, It's a constant, not a variable. We know what that value will be. We're taking -2, so you know, I'm just gonna finish this one and I'll go back to it just so I don't have to erase everything and put it back. Okay, just give me 1 second. So a plus b complement plus 1, and that happens when x is 0. And remember, that's just a minus b. And then the next one, a plus b complement, a plus a minus b minus 1, we'll simplify to a, I already wrote it up here, minus 1. We already proved up here that that just simplifies to a plus b complement. So really, we just have a plus b complement, which is this instruction here. And then we have a plus b complement plus 1. And that makes sense because when x is 0, we add 1. So for box 14 here, we're going to take b complement the 0th bit, b complement the first bit. All right. And now I will go back to boxes 5 and 13. So because -2 is a constant, and then we add 1 when x is 0 to get -1, -2 plus 1 is just -1. So let's take 0 or 2 in binary, which will be 0, 0, 1, 0, right? 2 to the 1 is 2. So take the 2's complement, 1, 1, 0, 1, add 1, 1, 1, 1, 0. So that's -2. Unless I'm going crazy, that's -2. All right. So that means we want to take the first bit and the 0th bit of -2. So that's the first bit and that's the 0th bit. So up here, this is the first bit of the result. So 1, 0, because that's what it is. We already took the complement. The complement of a constant is a value. It's just another value, right? So we're not going to complement it again, because then we'll kind of just be back where we started. Does that make sense, Waleed? Apologies if I didn't say your name right. All right, I'm not seeing, kind of. Okay. So I'll go over it one more time really quick. -2 is a constant. +2, 0, 0, 1, 0, that's 2. We want to get -2. So we take our 2's complement and it becomes 1, 1, 1, 0, right? That's -2. We want to add this value. We want to add -2 to a. And if we know this is -2, we can just put these bits into our multiplexer to get it. So bit 1 of -2 is 1. Bit 0 of -2 is 0. Okay. And if we go down here to the last one, this one's actually pretty simple. If we look here, there's actually no second operand other than that +1 that's taken care of by x. So we literally just feed a 0 into the last input. And then this box 8 here, this is just standard with any full adder. This is just your carry in from the bit before it. So this will be CY1 because that's our carry here. All right. Now, I don't have an answer key to this question, although I'm fairly certain this one's correct. I had a similar question on my own quizzes when I took this course. So I think we'll go ahead and say this one's solved, and I'll check it later for a mistake in case there is one. All right. Next, let's go. This is a practice final I have. I'm just going to go over some of the questions here. Also, I forgot, should have said this earlier. In the site Discord server, there's a bundle of documents that I posted in a PDF. These are documents that will be very similar to what you will be given on your final exam. To follow along, you're going to need them. So if you don't have it downloaded already, I'd highly recommend you download it. In fact, maybe we can even start it in the Zoom chat.
Yeah. Awesome.
Do you have a device with you at all, or you might want to have it open if you can? Okay.
Is it in your phone?
Right there.
Oh, it's right there.
Just send it in Zoom chat. Okay, so Ricky's gonna send that in the chat, and then we'll get started. All right. My calculator. Okay, so let's just start with Q1 here. This is a fairly simple multiple choice question, just testing your know. Oh, we have a raised hand.
Yeah.
Can you show that quiz question again? Sure, I'll show it really quick.
Is somebody?
It's a bit messy. I'm just gonna clean that up a bit. All right. Looks good for me. Okay, cool. So let's start here. This is just a simple question of testing your knowledge of basically how binary works. So for 1K, that's 1,000 memory locations. So we want to be able to choose between 1,000 memory locations, and we need to do that. We're going to need 2 to the n bits, right? So 2 to the n equals or is greater than 1,000. So this is like a ceiling or a floor function. I forget. Either way, it's not super important just because we can just, well, we only have a few values to try, right? Let's try 2 to the 8. I have a calculator handy, but if I just plug 2 to the 8 in, 2 to the 8 equals 256. Someone in chat. Yeah, it is. Yeah, the answer is 2 to the 10. I just want to explain why. So 2 to the 10, we'll try the next one. 2 to the 10 equals 1024. So 1024 isn't 1,000, but it's greater than 1,000. So we can just have a few empty memory load, and we can have a few like extra possibilities that we just don't need to access. So that means our answer is going to be, oops, that's not a highlighter. It's going to be 10 address lines, because if we have 2 to the 10 is equal to 1,024, and this is the smallest number of memory lines that gives us a value greater than 1,000. All right. And it's important to remember that address lines in this case is just like bits in your bus, right? So you need to have enough bits to be able to access those memory locations. All right. Which CPU register provides the address from which the next instruction opcode is to be fetched? So, okay. Yeah. Okay. I'm just gonna show what I'm gonna use in chat. But so this one's pretty easy because you were pretty much given the answer, because at the end of this exam there's an annex. Where is it? Oh, here. You can just see. Also, if you just know how, you have to have a bit of knowledge on how the basic computer works. But you see here, the program counter loads it into the address register, and then from there we start decoding what's going on in the address register. So the next instruction is fetched from PC, the program counter, all the way up here. There we go. Okay. This question, this is basically just an easier version of that question we did earlier. Do you guys want me to do it? We are semi-limited on time, so if you guys are comfortable with this, I'll just go to the next question. But if not, I can do it as well. What do you guys think, those that are in the room? Do you want me to go over this one? It's the same thing. The operations are different and there's fewer bits. Yeah. Okay, so we'll skip it then. Okay. So now we start getting into some more difficult basic computer questions. So this is just how to tell what type of instruction is going on. The real question is down here. So if we look down here, this is current, these are the current contents of our program counter. So we're told that, and we want to find out what's going to happen to those values after. So the instruction to be executed is here. Oops. 3AF. So that's an address. So 3AF is equal to 93AD. In questions like this, it's really important to have those diagrams out just so you can have an aid to know what's going to happen as you go through the computer here. Just 1 second, I'm just pulling one out here. Someone wants to join. Cool. Okay. Okay. So on T0, so we go through the cycle. This is normal. On T0, the program counter gets loaded into the address register. So we see here. Let's keep things quiet. All right, just 1 second. I haven't done this material in a while. I'm checking my notes here to get everything right. That's the basic computer. This is the yeah, I know. I just want to be careful this so we can make sure we don't make mistakes. Okay. So 3AF. So we're going to go to address 3AF. We know, let's just make a copy here. So this value gets copied into the address register. The PC to AR 3AF. And these aren't necessarily the final values. These can change just throughout one cycle, but we're just gonna, because I know the answer, so I know that it changes again. Either way. So we load the program counter into the address register 3AF. On the next one, we increment the program counter. So now what changes to the program counter is we add 1. So 3AF plus 1, that's just going to be 3B0. All right. And now what happens is we go to the MAR. So we go to the address at 3AF and we load that into the instruction register. So if we go here, 3AF, we have 93AD. So we load that into the instruction register. All right. Then what happens is we enter the decode phase. So we load IR, right? So now the address register gets used again. So we know that it's going to get wiped out. So what happens is bits 0 through 11 of the address register get loaded, of the instruction register, sorry, get loaded into the address register. So that becomes 3 F, right? Oh, sorry, no, it's a 3 AD. Bits, so bits 0 through 11, that's these bits here, because those are, this is in hexadecimal, so that's 4 bits, 4 bits, 4 bits. So 0 through 3, 5 through 7, 8 through 11. There we go, right? So that's 0 through 11. We load that into our address register. And then the 15th bit of the IR gets loaded into I. So if you were to go look at your chart again, you know that this is, so the last digit is going to be your opcode. And if the value is 9, then we know that that's an indirect add. So first off, it's indirect. We know that this is going to get set to 1. Excuse me, to 1. So we've done that. And we know that an indirect add is a memory reference instruction. So now we go here to, we're at time T3. We know that T3 I is equal to 1, so we enter our dereference phase. So what happens is you have the AR, oops, that's AB. And then you have MAR. And AR currently contains 3 AD. So we're gonna take M of 3 AD and load it into AR. So AR gets used a lot here. It changes a lot. So what's the values of memory at 3 AD? We have 03B5. So that means our address register is going to become 03B5. In fact, the address register is only a 12-bit register, so it's just 3B5. All right. So now we've done that, and now we start entering the, we can actually execute the instruction here. So we're at time T4 now. So if you look at your annex here, you can see that MAR gets loaded into the data register. And we know that AR currently contains 3B5. So that's the address we're going to go to. Let's go to 3B5. 3B9F, that gets loaded into the data register. Okay, that's that. Next, what happens? This is where we get to the fun stuff. So we have AC is equal to AC plus DR. So the accumulator contains 2EC3. And then we're going to add the value that's in the data register of 3B9F. Now, if you really wanted, you could, now in the interest of time, you could expand this into, you can do the addition yourself. I'm just going to make sure I get this right and plug it into my calculator. Just in the interest of time, 2E C3 plus 3B9F. So then that's going to equal 6C 6 2. This looks like I entered something wrong here, actually. Yep, I made a slight mistake entering in my calculator. All right, 6A 6 2. Can you, once you finish, can you recap? Yeah, okay. So we have the value 6A 6 2. That's gonna be the new contents of the accumulator. All right, there's no carry, so E will be 0. Oh, and then at the end of every cycle, the sequence counter resets, right? And I'm just comparing that to my answer key here. Yeah, we do have all the right values. So E is the carry. So if you get a carry in your operation, then your E would be set to 1. It wasn't. There was no carry though, so we know that E is 0. And E is a flag, but you don't really use that too much in this course. So what is the, now that we've filled this out, we can pretty much just fill this blank in here. What is the operation that will be fetched and executed? So as we said earlier, the instruction that was fetched was 93AD. And that's what we just, remember, what we did was an indirect add. So it's an, to say that in the language, add 3AD indirect. It's an indirect add from 3AD. So we don't go to the, we don't take the value at 3AD and add that. We take the value at the address in 3AD, so at 3B5, and we add that. And then show the operations in the binary operation that will be performed. So that was the operation we just did earlier. So it was the old contents of the accumulator plus the data register, which was 3B9F. And then C, I kind of did this question backwards just because I find that makes it easier to figure it out. But yeah, so fill out the contents. We just did that here. So to recap, really you need to have, if you don't have this document downloaded, I'm being serious, you really want it downloaded. You're not going to be able to solve the questions on your exam if you don't have that annex handy, and you will be given everything you need. The files that I uploaded were the files that I was given on my own exam. And I'm like, once again, if you don't have them handy, you will not do well on this exam and you won't be able to follow along today. So starting from the top here, what happens is you actually have that handy flow chart that just shows you what happens as you progress through the sequence counter. So when SC is equal to 0, I'll just run through this really quick, just keeping that here. When SC is equal to 0, the program counter gets copied into AR. So the program counter contains 3AF. All right. Next, program counter gets incremented. 3AF plus 1 is 3B0. All right. And you get the contents of this address. This is the address register. And if you look at the flow chart, it says M of AR into IR. So M of AR. Okay, so they were sent in the chat earlier, right here. And I sent them on Discord. And I'm looking at, can you just open the document there for me quickly, just so I can tell them? Yeah. So I'm currently looking at page 3 of that document with the flow chart. Oh, sorry, no, that's the wrong page. It's where is it? Oh yeah, no, it is. Yeah, it is this one, page 3. It's just a slightly more full chart. Okay. Does that make sense? Do you have, so if you don't get that, if you don't have it already, but yeah. So where were we? We were at P1. So we are take MAR is equal to MAR 3AF. Okay. Look, can you send it again, Ricky? Oh, maybe if you joined it late, then maybe it doesn't show the chat history. That might be why. Okay. So Ricky's gonna send it again, and then you can download it. Yeah. Yeah. If it was a direct, then it would just be add 3AD, just like that. Oops. No, the I, because it's like there's no D flag. It's just I. I is either 1 for indirect or it's 0 for direct. Yeah. All right, so Ricky, this was the annex that was literally given to me when I took this course last year. So it was just sent in chat one more time. We're just following the flow charts here. Thanks. Okay, you got it. Cool. Can you actually just open it for me as well, so I can have a second copy handy? Thank you. Okay, so what did we just do? Oh yes, so we're going to the memory. We're taking the contents of memory at address 3AF, and we're loading that into the instruction register. So 3AF contains this, which will go into IR. So that's our instruction register. This is the instruction that will be executed. It's in the instruction register. So we know that 9, the opcode, that's equals an indirect add. as you can see on page 1 of it, you can see that when you have 9xxx, that's an add, and we know that I is 1, so that'll be an indirect. So 9 is an indirect add. So add 3AD indirect. Okay. So we just dereference, not dereference, we just loaded a MAR into IR. So we go to the next cycle, T2. So IR, what we do, I watched on this myself. IR, we take bits 0 through 11 and load it into AR. So that's the address portion of the instruction register. So that's these bits. So 3AD gets loaded into AR. So we're overwriting this again. 3AF, that becomes 3AD. And then what also happens is if it's indirect, so that's IR 15, that'll be the 15th bit. That gets loaded into I, so we know that it's indirect, so that'll be 1. And then the instruction gets decoded here. You don't have to worry about the decoding. That's for hardware implementation. We don't have D0 through D7 registers here, so we can just ignore that step. Then we go down to the next part of our flow chart. And since I is 1, this is an indirect instruction. So we go to M of AR again. And remember, AR contains 3AD now, not 3AF. So M of AR contains 3AD, and we load that into the AR. So let's go to 3AD. There it is, 3AD 0 B. Where was I? Wait, no, that's something's not right. I just confused myself again. What did I just do? Yeah, I think I just got the wrong number here. Just 1 second. 3AF 93. Okay. Sorry about that. Just 1 second. It's hard when you're switching between screens like this back and forth. AR, just load into AR. So AR. .3AD. Okay, I confused myself. Still, yeah, just sorry. Just give me 1 second to find where I was. Yeah, it's also in the Zoom chat right now. CEG, in the CEG channel in site.
I'll send it to all of the servers that I'm in.
Okay, yeah. Ricky's gonna send it around again.
Because I'm people from other servers that I'm in.
IR contains. Okay, so at T, I'm just going back to where I was at T2. So instruction register contains 93AD. So the 0th, these bits of the IR get loaded into AR, so 3AD. All right, so AR becomes 03BF. We're at T2, yeah, I rewound a bit, just because I was. Yeah, that's exactly what, you don't add, you load, that's what happened. So it's not all of IR, it's bits 0 through 11 of IR. I have the memory M3AD. I'm at T2, and it says the instruction register currently contains 3AD. And now what happens is just not the memory of those bits get loaded into AR. So now AR will contain, yeah, so this is, yeah, I jumped around a bit and I got lost. You know what? I'm just gonna go back to the beginning here. I'm really sorry. I'm just gonna go back to the beginning and try to do this. No interruptions. Everyone, please have the annex handy because it is important. Okay, I'm really so sorry about that. Let's just do this one more time really quick. So PC from T0, PC gets loaded into AR. 3AF. Next, T1, PC gets incremented. And now M of AR gets loaded into IR. So M of AR, 3AF, is 9380. That value gets copied into IR. Next, we start our decode. So it's 0 through 11 of IR. So the address portion of the instruction gets copied into AR. And we know that 9380, that's indirect add. So we set our indirect bit to 1. All right. Next, now we're at T3. So M of AR gets loaded into the AR. So we replace M of AR. So AR contains 3AD equals 03BF. So the address register then contains 3BF. All right, and now we start executing the memory reference instruction. Can you open the annex again, please? So we go down to page, now we're at the memory reference instruction page. So that's page 4. We know this is an add. So we're at T4 now. So what happens is M of AR gets loaded into the DR, the data register. So AR contains 3BF equals, yeah, here, back on track, 3B9F. Okay, and that gets loaded into the data register. Next, you do your add operation. So yeah, you then add the contents of the data register to the contents of the accumulator. So the accumulator contains 2 EC3, the accumulator, that's the accumulator, the data register, 3B9F. All right, that comes out to 6A62. And then that gets stored in the accumulator. There was no carry, so E is 0. And then remember, that's the end of our instruction. Sequence counter resets to 0, or just 0, it doesn't really matter. All right, does that make sense there? So if you understand correctly, the memory contents first hex bit determines the type of opcode. It doesn't just determine the type of opcode, it is the opcode. All right, so let's I'm gonna open up the slides here, and that's a good point. We should go over that quickly. Oh shoot, I lost connection to my projector. It's back. Okay. So if we look at this slide here, it's a messy slide. There's a lot going on. But let's look through this. So this is a basic computer which uses 16-bit instructions. So here's the bits, I0 all the way through I15. So this is just, it shows when I15 is 0, it'll do that. I15 is 1, it'll do that. So remember, this is our indirect bit. Opcode is bits 12 through 14 of the instruction register, of the of the instruction. And technically, you can also consider it with the 15th bit as well. But just when you're doing a memory reference instruction, I mean, you know what? Yeah, it's actually easier to just take all 4 bits of that and just look for a corresponding value, right? So we have here these 4 bits, I15 through I12. So that's what we can convert that to a hexadecimal number, and that's what happened here. So this 9, that is bits 12 through 15 of the instruction. If we go to the chart here, there is a similar chart in the annex that was sent to you on page 1. It's the same chart. This one's just in color. If you look here, when you see a 9 in your first bit, that's an add, and I is 1, indirect add. All right. Now, let's say we have a special case when that opcode is 7. Then it becomes a register reference instruction, which means that the memory unit won't be accessed. And 7 is when you have 0, 1, 1, 1. So bits 12 through 14 are 1, but I is 0. And then when I is 1 and bits 12 through 14 are also 1, then you have 1, 1, 1, 1, which is F. So that's the opcode. First bit is the opcode. Now, it's important to realize that when you have either a 7 or an F, the instruction does not depend on any memory address. This is no longer a memory address. This is the instruction. So if you went back here, let's say we saw this was a 7, then the following values will be one of these. It won't be anything else. If it's something else, something is wrong either with the question or something you did. If you have a 7 or an F in the opcode, the following values will always be one of these because that's the entire instruction. So 7800 means to clear the accumulator. And you'll notice that all of these instructions do not need access to the memory. So that's why it's called register reference instruction. This one's an input output instruction. These aren't really used in this course, but they are still supported by the basic computer. All right, does that make sense there? Can you open the chat for me? Does that make sense? The first hex bit is the opcode. All right, I'm going to assume it's a yes. Okay. Now we start getting into the really fun stuff. So now we're basically interpreting assembly. So
I have a question
about which sorry? So the stuff I was just on? Yeah, 1 second. Yeah. So I will go over that in the last question because it's a very powerful instruction. What that means is ISZ. If we look at the flow chart, actually, do I have the flow chart handy? I have my own version of it at the end here. It's here. That's for the lab computer. ISZ. More. So yeah, okay, it's been a while since I've used this myself. All right. I should have I'm going to download this myself and open it here because actually the annex has the details of that instruction. Just the chat. Okay, so we go down here to our flow chart here. We can see what happens at ISZ. So you load the data register into the AMET AR. So you have an address and you store the data register at this, whatever is the address of the current address register. If DR is 0, what happens is you increment the program counter and then you reset the sequence counter to 0, which means we go all the way back to the top, right? So it's important to realize that the program counter gets increased right after it's loaded into the address register. So at T0, we load the current address into the address register, the current instruction into the address register, sorry, the address of the current instruction into the address register. And then on the next one, we increment it. So that means currently the program counter contains the address of the next instruction. ISZ, what it means is if the data register currently contains the value 0. Sorry, if you look actually at the screen there, what happens is the data register gets incremented. So that's that increment. So it literally adds 1 to the value of the data register. 0001. And however many bits it'll just be bit 0 is a 1, all the others are 0. It's literally the value of 1. Now this is really useful for counters, and we'll show that later. So what happened is if it's ISZ, you have an address. So it will take the value, it'll go to that address, take its value and load it into the data register, increment it, and then it will save that value back at the address, the incremented value. If it's 0, then it will increment PC. So remember, we already incremented PC, so it's at the next instruction. Incrementing it again will go to the one even after that. Yeah. So it's like it skips the instruction that was going to be executed next if the data register is 0. Does that make sense? Yeah. Okay, awesome.
The G6, G5, the data register was incremented. So down when we say if G5 is equal to 0, DC was incremented. Can it be 0?
Yeah, it can overflow to 0. Like if it's a negative value, if it's, because remember, -1 in binary 2's complement form is 1, 1, 1, 1. If you add 1 to that, what happens? 1, 0, 0, 0. But that 1 is a carry. It gets carried out. We forget about it. So now data DR is 0 because we don't have a 16th bit. Or sorry, we do have 16 bits. We don't have a 17th bit. So we do that 1 that got carried out just gets lost, and the DR now contains just the number 0. You understand? Awesome. All right. Let's go back here. Okay. I get my papers out here. So what is the result in decimal of the operation performed by the following assembly program? And then we actually have to turn that into machine code. So that's not too bad, actually. Yeah, so how should we start this? Let's just convert this into our machine code here. So again, super important that you have your annex here open, because you're going to need the chart with all the numbers that tells you what's what. Oh, I don't need this anymore. Need that. Then we need our opcodes open, which is the first chart, table 5.2 in the annex. So also, does everyone know how to read how this table works? This is what you saw in Quartus before. So this is your memory file. This is basically the program that will be executed in the form of machine code. Oh, you know what? I'll just go over it quickly. So you have an address, and then you have like an offset. So if this is address 0, address 100, this column 100 plus 0. So this is address 100. And then you have 101, 102, 103, 104, 5, 6, 7, and then next 108. It's a bit weird of how to represent it, but it does make sense for later on. If you actually start writing a lot of code, it starts to help just have in groups of 8, just because it's a power of 2. So remember, effectively, the program counter will just go through each of these addresses one by one, right? So ORG 100 means we're going to start at 100. So LDA OP. So this is an LDA OP1. Oh, it's just LDA OP, which means it's a direct add. So if you go look at your chart, you'll see, actually, I guess I can just show you here just what I'm doing quickly. Here, LDA gets a 2 for a direct LDA followed by the address. So, and OP is just a OP is just a what's the word? It's just a label for the address. So remember, what happens here is effectively that becomes address 100, 102, 103, 104, 105, 6, 107. Bit hard to follow here. Sure, where's the ruler? Okay, so okay, so ORG 100 just means the next instruction will be contained at address 100. So if we go OP, that's a label. OP is located at 107, and then LDA direct is going to be an opcode of 2, so that'll be 2107. And we were just given that to start. Next, CMA. Right there. So CMA, if you go look at your table, that's a register reference instruction. So we actually don't have any addresses to worry about. So now all that's going to happen is we just take the total instruction code for CMA, which is 7200. All right, next, INC. So INC is another register reference instruction. So that's 7020. Just looking at that chart again. All right. So we did INC. Add OP1. So that's a direct add. So a direct add has the opcode 1. And then the address of OP1 is 106. STA OP2. So STA has the opcode 3. OP2 is at address 108. HLT, that's halt. HLT has the code 7001. All right, now we're at address 106, and we just see here, so we just take the value. So remember, OP1 is just a label for address 106, OP a label for 107, and so on. So address 106 just contains literally the values we're given here. 0, 3, 9, F, A, 5, and then OP2 contains a 0. And that's the end of our program. So it's safe to assume that we just have tons of zeros, assuming that it's an empty file. All right, I'm not going to waste time and fill out zeros and all of that. It's a label. Yeah, so OP1, these are just labels for the addresses that we were given. So now we actually have to, now that we filled out the chart, it wants us to figure out the result of what's going to happen. So LDA OP. So load, we're going to load the OP is 107. So the value at 107 is FF85. So the accumulator will contain, excuse me. So AC will contain F A 5. All right, CMA. So yeah, I'm just gonna actually, I'll keep doing it over here just so we can keep track. So everything below down here will be the accumulator. So it's a bit far away. So I'm gonna keep the contents of the accumulator down here. So FFA5. So we're loading OP. OP contains FFA5. The accumulator gets FFA5. We take the complement of FFA5. So I know that F is 1, 1, 1, 1. So the complement of that is 0, another 0. A would be, yeah, I'm just gonna make sure, just 1, 0, 1, 0, which would be a,
Yeah, 1, 0,
1, 0, 1, 0. All right, cool. And then that in hex would be 5, right? 2 to the, just 1 second, sorry. Yeah. Yeah, okay. So yeah, it's 5. And then the complement of 5, well, that's A. We just do the same thing in reverse. Cool. All right. Increment. So we increment the accumulator by 1. So A plus 1 is B. All right. And now we add the contents of OP1. This becomes 005B plus add OP1 0039. This is my calculator. So 5B. That becomes 0094. All right. And now STA at OP2. So we're going to store the contents of the accumulator at address OP2. So OP2 is 108. So that means M OP2 0.4, yeah, M of OP2 equals 0094. I just said this column is the accumulator, so I'm just doing it off to the side. And then we halt, right? So that's our value here. So that's our final answer here, because, well, that's what's in the accumulator as well, right? And then that just got stored at address 108, and which just contains 0 right now. So the final value 0094. I'm gonna say it wants it in decimal. So hex of, we're gonna say 0x94. That's shorthand for hex. We want to convert that to decimal just because that's what the question's asking for. It's asking for the result in decimal. So 9 times 16 to the 1. Oops. 9 times 16 to the 1 is 144. 4 times 16 to the 0 is just 4. And there's our final answer of 148. But what is OP, OP1, and OP2? So as I said before, these are labels. So when you are writing actual assembly, it can be really hard. Imagine you were writing a program in C or Python and you weren't allowed to say, okay, I want to have a variable named A. I want to have a variable named CTR. Imagine you weren't allowed to do that and you just had to write in a number that's the actual address in memory of that variable. That'd be really annoying. And that's kind of what you have to do if you're writing in just machine code. And it's just really hard to read this because it's all just numbers. So when you turn assembly into machine code, it's a one-to-one translation, just because, as we said, LDA LDA is just opcode 2. And then OP is a label for this address. And as we said before, ORG 100 means the next instruction is at address 100. So we just fill out this table. So that means OP is a label for address 107. All right, make sense? And same thing here, OP1 would be an address for then 106 and OP2 108. And then these values here just shows the memory contents of those addresses. Okay. Good last year. Oh, okay.
That was on-
I guess so. All right then. So any other questions regarding this? So the final answer is 148, and we'll just say that's in decimal. Check the chat. Oh yeah. Okay. So remember, OP1, OP2, OP, they're just labels. They're labels for for just an address, which is a number in memory. All right, next. So this one is a question that's kind of similar to what was done in lab 4. You have to generate the control signals for these new instructions. So oh wait, actually no, this was the question. Actually, I think we're gonna skip this question just because this question was just insane and I was never able to solve it, and we never even saw anything like it on the exam. I really don't know why they would give a question like this. Yeah. Yeah, I never solved this question, and looking at the solution, it doesn't really help either. So we can just go right on to question 5. Okay, yeah. Yeah, no, question 4 was insane, and I never really understood how to do it. And looking at my exam, we never really saw, we never got a question like that either. Like, if you want, I can pass the solution around. Here, I can just show it to you. It's a very Rosa slide. It's very hard to follow along. Yeah.
Yes, Rosa.
And this is actually 2 different ways to solve it. He was so generous to give us 2 solutions. Neither one is more clear. So I'm gonna put that back there. Okay, question 5. Now question 5 kind of builds on, you just need to know this. You don't have to have the data path built. It's just, it does semi-build on it, but it's not that bad. So this one really is just testing your knowledge of the fetch, execute, decode cycle. So again, as I've said too many times before, someone's in chat. Okay, as I said way too many times before, you need to have the annex, otherwise you're gonna get screwed. So, and you also just need to kind of have you also need to have a general understanding of how the fetch, decode, execute cycle works. So remember, PC into AR. So what does the program counter contains? It contains the address of the instruction to be executed. So back to this one, I'm just going to type just so we make it a bit clearer. Oh, no, chat. Where's the solution for 4.2? Okay, so yeah, I didn't upload the solutions. I'm not sure. I mean, he did give it to us. If you want, honestly, don't worry about 4.2. Do not worry about it. I'm serious. It was insane. I never understood it. Like, I could just show it to you, but I don't understand it myself. So we'll send it after. Okay, so when you say at T0, so that's the fetch cycle. It's the fetch portion of the cycle. So the address of the instruction to be execute loaded into AR. All right. Next, loaded into AR. So the yeah. So now M at AR. So we're going to that address in memory, which contains the actual instruction. So the instruction is loaded into the address, into the instruction register. And what just happened? Program counter is incremented, and which is for the next cycle, address of next stored in PC. All right. So now here again, we have the decode phase. So if you look at the actual hardware path of the basic computer, what happens is it takes that opcode, so that the opcode, and it decodes that into 7 distinct values, just so that it makes it easier to later on when you want to actually control your registers. You just say, okay, so I know that for this opcode, I need this register to change. And when we're using this opcode, I just know that D7 will be high or D1 will be low. It makes it easier than just having to go through the logic for the opcode every single time. So instruction opcode is decoded. AR, IR 0 through 11. So address of the operand. This is for a direct instruction. Or pointer. Indirect thing loaded into AR, and then next, if direct addressing I bit is set to 1. All right, and now here you see this I. So this is at T3. So at T3, if I is equal to 1, then we actually do that dereferencing type thing where we go to the address in the address register. So if the address register contained 004, then that's not the value you're going to work with. Then you're going to go to address 004 in memory and then take that value. So direct addressing. All right, so that's that. All right. Dereference. So in C, if you have a pointer and you want to like take the value that's at it, then you dereference the pointer. That's actually what's happening here. So let's go back up here. Let's go up here again to this thing, 9380. So we've established this is a add 380 indirect. So the accumulator contains AC C3. So when we say add 380, it means we do not go to 380 and add 3B5 to it. So remember, so 380, the address of 380 contains 3B5. That's not what we're doing. Instead, what we do is we actually go to address 3B5. So down here, 93BF, or 3B9F, sorry. So that's what this is the whole indirect thing, right? So you do, so yeah, if you go back and look at this question in the recording, it'll be a bit more clear. Do you have does that kind of make sense for now, or? Okay. Next. Use RT, okay, yeah, this question. So this question is pretty tricky. This is kind of what happened in lab 4 again. So if you go, what happens is you go look up here, right? and we're basically want to make the control signals that would be necessary for this to happen, right? And if we look, it's also important to have the annex open again, so you can see the map of the basic computer. All right, what was this? Okay. So you want to have that open. So this new instruction, ASR, which is arithmetic shift right, dr/d2. So what's going to happen? Just give me 1 minute just to review this question, because I forget this one as well. Oh, actually, yeah, I don't think, no, for this to work, you would actually need you would need to have done question 4, but again, this really wasn't given to us anything like this. This question was just pretty crazy. So I think we'll leave that for now, and we'll go to this question here. Because what happens is you have to have figured out what the logic looks like to be able to implement these instructions, and then you have to set those control signals. So we're going to skip this one. So now this is some more easy questions. This is another, this is just a full ladder question. This one's pretty easy. So question 1, consider the following logic diagram. So it's giving you some questions, and basically you're just going to feed those values into this logic and see what happens. Now, you should know by now that this is a full ladder circuit you probably remember it from digital systems, with a toggle to turn on subtraction, right? So by setting M to 1, it'll complement B, and it will add 1 in. So remember, that's 2's complement, because minus B equals B complement plus 1, right? So that's all this circuit does. So we're gonna start here with this first operation here. So all we're gonna do is pretty much figure out what's gonna happen. So we know this is a full ladder. So 1 1 0 1 plus 0 1 1 0. All right. And we know that it's just this. We're just leaving this value on its own because M is set to 0. We're not complementing it, taking the 2's complement. So just normal addition, 1 1, then 1 plus 1 is 0 1 0 1. So we carried out a 1, so that's C4, that's our carry out. So we carried out a 1, and then here's our result of addition. So that's 0 0 1 1. Okay, makes sense? Perfect. Now we will do the next one. So 1 1 0 1 is A, and here we have B. And remember, B, we have that M bit set to high, so it's B gets complemented and then plus 1. And also what happens here is this is the complementing logic, right? Because if you have X XOR 1 or XOR 0, actually, let me just draw the truth table for XOR gate. So 0 XOR 0 is 0. Remember, this is exclusive OR. So that's what the logic looks like, right? So if you have a 0 and your XOR is 0 and your M in this case is set to 0, so we'll say A XOR 0. Just look at these two columns here. Oops, no, that's not what I wanted to do. A XOR 0. Just look at these two columns here. So if you have your B, we're treating the this value as B here. So 0 XOR 0 is just 0, and 1 XOR 0 is just 1. Or it's like saying A XOR 0, A stays the same. But now, of course, if you do the other one, oops, nope. A XOR 1, it gets complemented, right? So 0 XOR 1 becomes 1. 1 XOR 1, it becomes 0. So that's what happens when you take a value and pass it through an XOR gate where it's just 1. It complements it. And of course, the second branch of this will always just be 1 or 0. So you know that it's either going to stay the same if it's 0, or it will complement if M is 1. In this case, M is 1. So take the 2's complement. Or just take the first, we just take the normal complement. And then add 1 to it, because we have that carry in. 2's complement. All right, so now. Where did the answer go here? I make a mistake here. Okay. Plus A. So our answer would be 0, 1, 1, 1, again with our carry out. Now, it wants us to basically check if our answers are correct. So these are the values of the resultant binary. We have 0, 1, 1, 1, and 0, 0, 1, 1. I'm just going to drink some water. All right, so we have our answers in binary. We don't know if they're actually, if we had overflow or not yet. We just know that those are the answers that are present in the logic. So it wants us to convert A into decimal. So 1, 1, 0, 1. In decimal, that's going to be, what will it be? It will be, oh yeah, so it's a negative. So we should take the 2's complement of it first to turn it into a positive number. So the 2's of that negative will be 0, 0, 1, 1. We convert that to decimal. I know that that's -3. -3. All right. And B here. So do B, so the 2's of 0, 1, 1, 0 equals -1, 0, 1, 0. And then that value would be oh, sorry. Yeah, this question, the table's not in a great format just because they want you to like do it twice, but then it's a bit strange how they've set it up. But either way, for the second value, M is actually 0. So we're not going to take the 2's complement. So 0, 1, 1, 0 in decimal would be 2 to the 2 is 4, be 5, right? Oh no, sorry, 6. Yeah. Yeah, you're right. So we have 6. And then, yes, yeah, so it is positive. So the 2's complement is going to be the same. You're right. I tripped myself up there. As we said before, we're not taking our complement. And then we carried out, and our result 0, 0, 1, 1 in binary. That's 3. Or in decimal, sorry, that's 3. So that's 3. Let's check if that's correct. -3 plus 6 does indeed equal 3. So that's great. That's right. Awesome. Next one. Okay. So again, we have that same, A is the same. So for the second one, we still have -3. And now we have our, we're taking our 2, we're complementing this value to make it negative. So 6, we want to make it negative, that will become -6. All right, we said, as we said before, M was still 1, we still did a carry out. A 1, okay, so this is going back to digital, yeah, ITI, what was it, 1100 digital system. So this is 2's complement notation. So remember, 1101, that's our sign bit. A 1 in the first bit, because we're taking this as a 2's complement notation, as it says here, 2's complement representation. So that's going to be our sign bit. So we know that this is a negative number. If we wanted to turn it into, now it's important to realize that just because of how 2's complement works, it's not just minus and then whatever the following values are. So it's not -4. All right, 2 to the 2 is 4, yeah. So that does not equal -4. If you want to make this, turn this into a decimal number, then what you do is you take the 2's complement of it again. So it would be, oops, it should be a 1. So flip all the values, add 1, attach a negative sign, and then we can just convert that to decimal. That's -3. This really goes back to digital systems, so I don't really, it is given that this was the prerequisite for the course, I don't really have the time to go over 2's complement notation. I do expect that you understand that at this point. So that was the course before this. So we established that this is -3, this is +6, or negative is +6. Yes, exactly. For a bind, if it's stated that it's in 2's complement notation, which means it has a sign bit. If you want to find the decimal value, then first you have to, the best way to do it, if you're not allowed external tools, which you're not, assuming, at least I'm assuming you're not, would be to convert it and take its 2's complement again. So I'll just go over that one more time. So here's our A. We see that we have a negative, a sign bit, so we want to take our 2's complement. So flip all the bits, add 1, and then convert it to decimal. So I know that that's equal to 3. And then just remember that we had that sign bit before. So we have to attach the negative signs.
If I remember correctly, there's something called signed complement.
There's no such thing as unsigned 2's complement.
Oh.
Yeah. 2's complement is signed, always. Always. Because otherwise, there would be no 2's complement. The whole thing is to get negative numbers.
Yeah.
So
if there's a 1 in front and it's signed, and if there isn't.
If there's it's now just because there's a 1 in front doesn't mean it's signed. It's all about interpretation.
Yeah.
So I could so technically this number, depending on what the context is, would be 1101. That's what's that in decimal? Yeah, good job. What's it now? It is 13. So that if we just took that as unsigned, then that would be unsigned normal notation. We can say that's 13.
Yeah.
But as we said before, it tells us in the question, where did it tell us? Yeah, 2's complement. So we're taking this, we're assuming we understand that this is in 2's complement format. So since we see that one bit, if we want to turn it into the decimal by hand, then you take the 2's complement again and then attach a negative sign after you've converted it to decimal.
So we never just establish one and the rest and say, okay.
That's correct. In fact, that gets really important in computer architecture too, right? There's because most people in this room who have taken their course, we've gotten all tripped up. There's literally a question where basically you can, is this a carry or is this an overflow? And that like a carry is kind of like a different type of overflow for unsigned numbers.
Yeah.
I'm going to show you here what happens, right? So let's just keep going with the question. So again, we have our 0, 1, 1, 0, and we're going to take its 2's complement because n equals 1. So we want to make this negative. So that means, and then add 1. So that's 1, 0, 1, 0. And then we already did our addition. Actually, I don't know why I'm saying that here again. Another way, what was I doing? Oh yeah, so I did the addition up here where we already took its complement, added it together, and we got this value. So 0, 1, 1, 1 in decimal is +7. All right. -3 plus -6 equals -9, which is very clearly not 7. So something's up here. What happened is, since we only have 3 actual values available for data and the other's a sign bit, the largest value you can really have with 3 bits is 7. 1, 1, 1. So, if you go into the negatives, it becomes -8. And since we've entered an overflow, so we know that we've converted our values here. So again, how I got this value, just converted this to decimal, converted this to decimal, converted this to decimal. Here, same thing. It's the same number, just the same thing. We're saying 0, 1, 1, 0, but we took the 2's complement of it, made it negative, so it becomes -6. And then we just took our result and put it there. But of course, something's not right because -3 -6 is not -7. It's not +7, sorry, but it's also not -7 as well. So that's our answer, really. So the first one's correct, so we can just say, sorry.
-8 is -8 in sign representation.
-8. Actually, kind of. Again, it's all about context. So that's where it gets weird, right? And it is. Okay, I'll go ask that answer. So yeah, this is where it does get weird, because if you were to take the value of 8, 1, 0, 0, 0, so that's +8. And you want to take -8. Remember, you flip all the values and then add 1. So that's 8, right? So now to take the 2's complement. But remember, +8 is outside of the range of this. So really, so that's why this is actually -8, depending on what your interpretation is. So you flip all the bits, add 1, right? So because we've established that this is 2's complement notation, since we have that 1 in front, and then we can establish that it's a sign notation. That is a -8. Should we put -9 in the last box of the second table? No, it should be 7, because it's asking for what the values that came out of the machine are. And we established up here that this plus this, after you've taken its 2's complement, you've made it negative, is this 0, 1, 1, 1, which is 7. And it says, are your results correct? You're going to say B is not correct. Overflow. All right, so we know that it overflowed. Expander adder of a circuit that can signalize overflow. That's actually really easy. All you need to do, so general rule, I'll type it out actually. Well, first I'll just draw it. basically for any full adder, so this is a 4-bit full adder. You take carry, so for n equals 4 in this case, for an n-bit adder, you XOR the carry of n, carry n XOR carry n minus 1. Now that looks like really weird, equals overflow. This is from digital systems though. So again, what that means is this is a 4-bit full adder. I spelled adder wrong. That's embarrassing. All right. 4-bit full adder. I'll just draw this over here. So you're going to take n. So n is 4. So carry 4. It's a really sad XOR gate. Wish they gave more room here, but whatever. All right, so that's overflow detection. So you just remember this. Remember this. For an n-bit adder, overflow would be, if to detect overflow, you take the carry out of n, the nth bit, the last bit, XOR that with the carry before it. So for a 4-bit adder, n equals 4, take carry 4, XOR it with carry 3, and that's overflow. All right. Stop. So yeah, that's it for overflow detection there. Yeah, so you the correct answer now, -3 plus -6 is -9, but that's not what our full adder returned because an overflow occurred. All right, you would need more bits. So you could do that with a 5-bit full adder, although usually whenever we have you pretty much everything you do in computer architecture and digital systems, it's going to be to the power 2. It's like you'll have a 2-bit full adder, a 4-bit full adder, an 8-bit adder, 16-bit. You'd never really see numbers that aren't powers of 2, just because it goes down to binary. That it's the 2-bit system. All right. How are we doing? Okay. I think we can just take a 5-minute break just because I need to use the washroom, admittedly. So stretch your legs. We'll be back, and then we'll finish off this practice exam. Yeah, take a cookie too. We have lots. All right.
ITI 11.
All right. I'll be right back.
Mute yourself. Are you muted?
All right, guys, let's continue off. Let's continue where we left off. So we were at just starting this question. Let's read the question here. Oh, okay. This is question 3. Assume, find and derive the list which change the address row in RC. Oh, okay, I see. All right, just one moment here, just looking through question. Y0. Okay, so this question's not too bad. All it's asking is, based on the computer in lab 4, find all the micro operations that change the value of register AC. So what's going to happen is you're, again, going to go look at your charts, your lovely charts, and you're going to find all of the micro operations, so all of these that change the values of the accumulator. So whenever you see something like here, right? So that's a change in the value of the accumulator. So this one's pretty simple, actually. So we just go back up to the question. Can you open up the annex for me? It's actually, it's not in that. Okay, so actually, this one, I didn't actually give you the document for it, so that's not great. Let me grab it out here. This one, on the final I wrote, you didn't need this paper, but on the practice one here, you do need it. Yeah, here, why don't you take a picture and send this to the Zoom chat there. All right, so we're just uploading the necessary tables to complete it, this question. That's fine.
I can see this all in a Google Drive.
Honestly, just upload the pictures to the Zoom chat because then everyone will have them. X1 here. Sorry, just one moment here. I'm just kind of refreshing myself on this question. LD accumulator, increase accumulator. Let's do AC. I think there's a. I think that there might actually be a mistake in the solution I have here for this question. Something's not right. Just 1 second here. Nope. Yeah, I know. That's fine. I just did delete this. This is the solution that I came up with the last time I solved this. We go down here.
Are you gonna send that the whole solution?
Hang on just one moment. Y1 plus Y6. Oh, right, it gets simplified to that. All right, so for this question, all you have to do is go look at the micro operations table for the lab 4 computer. And then you find all the times that AC gets changed. So AC, remember AC has three inputs. So it has your load, or 3 controls. It has load, it has increment, and it has clear. So let's look at every time we load into the accumulator. So if we open that up, that, yep. So let's load this up. I open, oh wait, I don't know if I'll be able to open this file because it's like an iPhone format. Let's see if it works.
I can change the format.
Oh no, it worked. Okay,
Oh,
cool.
because I put in the.
Okay. So you want to find all the times that the accumulator gets. You can load into the accumulator. Did you take a picture of the second one too? That one, it is. We're just getting pictures of the documents we need here. Sorry about the wait. Okay. This one. And I need. Actually, which lab was your lab for? Was it, so you had the accumulator, you built like an ALU in the first lab, and then the lab 4, you assembled a whole computer? Is that what you did in this course, or did they change the labs?
I think it's
was already assembled and you just have to control the.
Yeah, okay, perfect. So yeah, that's it's the same thing here. So this is actually basically from the lab. Where did it go?
Oh,
What? Oh yeah.
I totally forgot. We wanted to watch this.
Well, you can watch the recording. So we look at this. We have A7. Okay. 30. That's the next question. We're not looking at that right now.
Oh, okay.
Oh, you sent it. Okay, cool. Download. Okay, so we want to find all the times that the accumulator gets changed. So as we see here, we have a load into the accumulator here. Whenever we see the dash into the accumulator, that's the load basically, unless it's like a 0 or an AC +1. But as you can see here, AC, so we see the control signal here at time 7 Y0. So we're going to sum up all these. T7 Y0, another one, T7 Y1. Next one, Y5, where is it? There it is. T7 Y5, T7 Y6. So we're going to sum that up. And then we also have another one, which is down here. So we have this one, it's a special case, that's clear, so that's 0, so we're going to ignore that. But we have this one, T3X1 IR1, T3X1 IR2, T3X1 IR3, and then again here, that's our special case, that's our increment. So all we need to do here, we found all the times when we enable a load into the accumulator. So LD of AC is just going to be T7 Y0. You're just literally adding all these up. T7 Y0 plus T7, oops, in chat. Yep. It's not TZ, T7 Y1. Not that. T7 Y5, try this one. Nope. And then I keep making this mistake. 7 Y5 T7 Y6. I keep saying TZ. Okay. Y6. And then we go to our the next one in the register reference instructions, where we have plus T3X1 IR1 plus T3X1 R2 plus T3X. That's the exactly. I'm just but I just want to list it all, and then we can simplify it just so. 1, 2, 3. All right. So now, yeah, as we said, we can simplify this. All of these have a T7 attached to them. And all of these have T3X1 attached to them. Oops, my X1. All right, so that's put a nice big bracket there. That's it factored. Next one, we can increment it. This one's pretty easy. We only ever increment AC once. And that's when we actually execute the increment instruction, which just has the control signal in table 3 of T3 X1 I excuse me, IR4. Yeah, I'd love some water. Thank you. Okay. And then we have our clear, which is another special one because we only clear it once during our clear instruction, which is IR0 CLA. X1 IR0. All right, there we go. Derive the logic equations. Okay, so yeah, that's it. It just asks for the list there. List. Okay, so yeah, basically I kind of skipped ahead by accident. Basically, question 1 would just be list out all these terms individually. Question 2, factor it out and then write out the logic equation. Does that make sense? Yeah. All right. Question 4. 2 memory reference instructions in the basic computer are to be changed to the instructions specified below. So, this.
That means that instead of the instructions that correspond to the output 1, we're gonna have this new instruction.
That's exactly it. Very good. So what's going to happen is, and this question looks pretty daunting, and it's not as if you kind of understand what happened in lab 4 though. It's not too bad. Oh, you know, I'll be honest, it comes into play. It helps, but study your labs. If you understand what's going on in the lab, you'll be pretty good, pretty well set.
We know Fortis sucks, but deal with it.
Deal with it. I would love to go back to Compark 1. It was so much simpler.
Yeah,
Compark 2 is hard, man. It's crazy.
the labs are really cool though.
The labs are easy, I'll be honest, but it's just C programming. Except for the first lab, we did a little bit of like assembly, which is kind of hard because it was a whole new syntax. It was a reduced instruction set syntax of ARM assembly, so it was a bit different, a bit weird. You had to learn some new ideas, but then the rest, if you've taken like ITI 1121, it's kind of like that, but a lot easier and in C. Yeah. Well, I've taken it because I've switched into electrical engineering and computing tech. But yeah, if you're in, but even if you haven't taken it, you'll have taken the C course and you'll still be fine. I still reference GNG 1105 or 1106. It's one of those. Either way, let's get back to this. That's so funny. Okay. So question 4. So what we want to do, so it's also, what? That's it. Okay. So what's up? If you remember, in the, also this is in the basic computer. If you look at the basic computer, hey there, what's up?
Oh, you guys came back.
Hey, is
Oh,
that Sean? Who's that? I can't see. Okay. Hey. Okay, either way, sorry. So remember, the execution cycle of the basic computer starts at timing signal 4. Before timing signal 4, it's just, here's the chart. So this is T4 here, and that's when the execution cycle starts. So if we want to change an instruction, because all of this is all common to every single instruction. That doesn't change because that's just fetching from memory, decoding it, and then passing it on to be executed. So we're starting at T4 here. And if you look at this table, where is it? That's lab 4. You want basic computer. If you look here, here's all our execute instructions. So you have, okay, the control signal D0, which corresponds to and that's T1. It's important to remember that D0 is like decoded from the opcode. So 000 is the opcode. That's D0. 010. That's D2. Yeah. 0, 1, 2. Yeah, that's D2, and so on and so forth. So 111 would be equal to D7, which then gets passed on there. But we were given these new opcodes here. So where did it go? Right here. We were given these opcodes. So we'll start with ADM. 001 equals 1 in decimal. So that means that the control signal for that, we're going to call that D1. So it's going to actually be replacing the instruction for add. So that's what this one's replacing. So what we want to do is add AC to memory. So how we're going to do that. So D1, T4, just we know that it's D1 because that's the opcode, and it's T4 because that's the first timing signal during the execute phase. Oh yes, and we were given some extra conditions here. It says that the value in AC cannot be changed unless the instruction specifies it. If that happens, then we get to use this special register TR to store as a temporary register to store the value. So basically we need the accumulator to be the same before and after. So what this means is if we need to change it, we just copy the contents of the accumulator into TR, and then after we just copy TR back into the accumulator, just so it's like nothing ever happened. So what we can do first, copy back up our accumulator. T. So back up the accumulator into that. D1, T5, next timing signal. What we're going to do, we want to copy the we want to copy this address EA into the accumulator. Now it's important to realize that to get into the accumulator, you have to, here it is. The accumulator isn't directly connected to the memory through the bus, right? So it doesn't have a direct input from the bus like the others. But what it does have that no other register has is a direct connection to the data register. So what we can do is first we can load, I think I got that wrong line there. We can first load it into the data register and then just on the next cycle, copy the data register into the accumulator. All right. So what we're going to do on T5, so data register. All right, copy the contents of memory at EA into the data register. And then we will add that. And then what we want to do is add that value. We want to increment that value by whatever is in AC. But of course, we can't add it inside a memory unit. What we have to do is we have to add it inside the accumulator. Pardon me? EA is just a label, exactly. It's an address, it's a label, but in text form. Where was I? That's T5, T6. We'll add. You're welcome. Good luck on your exam.
Different example.
All right. Is that an insult? I know, I'm just, it's like when you say you too to the waiter, you know? All right, let's keep going.
You're just so complimentary.
All right, why are DT1 and DT5 different in the annex? Okay, so as I said, we are making new instructions. So we're completely replacing the opcodes that's at DT1. This we are taking whatever's there and scratching it out because we are making a new instruction. We're replacing these instructions with these. So DT6. It looks like my printout got a bit messed up here, but what's going to happen is we're going to add AC plus DR and store that in the accumulator. D1, T7 is we then store at EA from the accumulator. Running out of room. D1, T8. We can then back up our sorry. So now we want to restore the accumulator to its original value. Remember, we can't just load right into the accumulator from this register. We have to load it into the data register first. And then D1, T9, running out of room. AC, load into AC from data register, and also reset the sequence counter. That's a little trick one because that's a good way to lose a point if you forget to reset your sequence counter. Why did you choose D1? I chose T1 because we were given this opcode. So, and 001 is 1, and that would get decoded into that D1 signal, as this will get decoded into D3 when we do that. All right, comments, I've kind of went over it verbally. I can type that out after if we want. I think we should just continue on for now. If AC is less than 0, then copy EA into PC. Okay. So now the actual solution they gave here, what we get to do is, remember, if it's less than 0. So any number that's less than 0, because if it's less than 0, it means it's going to be a signed number to have a negative number. That means it'll be a negative number. That means our signed bit's going to be 1, right? So if AC bit 15, because that's the last bit in a 16-bit computer, you have bits 0 through 15, and that's our signed bit. AC 15 equals 1. Then load the address register into PC, and we can do that because we can assume that EA was loaded into the address register already because of the fetch, decode, execute cycle. And then remember SC to 0. And I forgot my code here. All of this happens with the control signal D in this one cycle, D3, T4. Yeah, we use a decoder. How do you determine the opcode for Ds? Well, we were given the opcode up here. And if you go back to the basic computer, where is that chart here? So let's just take this random one. We'll take BSA. BSA, we have D5. And then we have that, which is going to be a 4 or C. And that's not actually BSA. I circled the wrong one. It's there, 5 or D. So the hex code is 5. So our opcode is so we have 5 that. So that's our opcode. 5 in binary is 0. That's 5 in binary. Help me out here. 0 1 0 1. Right. 2 to the 2 is 4 plus 1. Yeah. 0 1 0 1. So, and that is actually we didn't even do that. What am I saying? We have here 5, and then we just we get told here that gets turned into this control signal D5. When the opcode is 5 or D, the control signal that gets decoded is D5. When the opcode is 1 or 9, the opcode that gets decoded into the control signal D1. So, and remember that, so for our example, that 1 is 0 0 1. That's what 1 in hex is in binary. And that's what we were given as our opcode. So if we go up here to the question, we were given 0 0 1. So this instruction has the opcode 0 0 1 1, and that gets decoded into D1. So that's why. All right. So this is messy, but yeah, I'll upload the solution after, and all of that gets decoded into the answer there, which is D4, just because 0 1 1, that's opcode 3, which means it gets decoded into D3, that signal. All right. So the right number of D is actually the opcode in hex. Yes, although it's the direct one, just because it will use the same, the indirect one will use the same control signal. Pardon me?
Mhm.
Oh yeah. Okay, yeah, we'll get to the last question. Yeah, I think we are running out of time. What time is it?
It's almost 3:30.
Okay, yeah, we're gonna go, well, let's go to the last question then. Just because there will definitely be a question like that here. This question, all it's doing, we've kind of done a question like this already. It's just giving you a bunch of memory addresses and their contents, and then it's asking you to just figure out what the computer is gonna do. We kind of did that earlier with that whole 9-3AD question where we added from accumulator. The solution here is in the file I'll upload after. So I'll just upload that and you can study that on your own. We're gonna do this last question. Just because this question that you will it's very likely that you'll have something like this on the exam. Question 6. Following is alternate. Okay, yeah. This one I can just type. So we're gonna write assembly. Hooray. So, how should I do this? You know what, maybe I'll just write this in Notepad so I can, it'll be a bit nicer to type with. All right. So write a subroutine in assembly language that will multiply two positive numbers by repeated addition. For example, to multiply 6 times 4, the subroutine evaluates the product by adding the multiplicand 6 4 times. So it'd be the same thing as writing 6 plus 6 plus 6. We are allowed to use the instructions from the basic computer. So that's table 6. So that's this set of instructions. We can use all of these. We don't need all of them, but we're going to look at them. All right. 6 plus 6 plus 6. For invoking, we're given some conditions. So these are where the values that we get to work with are. So the multiplicand, in this case 6, will get stored at the address 9FF, and the other value we're working with 4 will be already in the accumulator. The result is passed by the subroutine to the calling program through the accumulator. So when we're done, we store the result in the accumulator. So we just don't want to clear it or anything like that. So that's wrong paper. All right, so oops, I'll come back. Just give it a second. Let's start. So the -f. So okay. Your subroutine should be stored in the memory of your basic computer, beginning with address A00. No, okay, one moment just to read up here. Okay, so the origin is at hex 9FF. Multiplicand is stored. Just 1 second. I just want to read this just so I can make sure I don't make any mistakes. That NLP. The multiplier is in the accumulator. Okay. All right. So we start with our we start with this instruction of origin hex 9FF. So again, all this means is that the next instruction or the next line of the program will be stored at address 9FF. The hex just means that this is a hexadecimal number, which should be obvious considering it contains F twice. So MLP, we can just set that to 0. So I don't know why it says that. That shouldn't be right because the multiplier is stored in the accumulator. Okay. Let's go with it. Okay. 0. Okay, those are just labels to those values. Just give me one moment. Thank you. All right, I'm not too sure why they say MUL 000, considering that that value is stored in the accumulator. Either way, we'll just leave it in there and you'll still understand the general idea of what's going on. So in general, to make a loop of a value, what you can do is, so in this case, we're making a loop. We want to loop through however many times. So in our example, the multiplicand or the multiplier is 4. So we want to loop through 4 times, and the multiplier was stored in the accumulator. So in general, to make a loop, what you can do, we want to loop 4 times, store 4 in the accumulator, which you've already done, complement the accumulator. So that will complement it, and then increase it. So then you have -4. So -4 is stored in the accumulator. And then store this -4 at a value CTR. And we can just have CTR somewhere else in the program at the end, right? Now clear the accumulator. Then what we want to do is actually, I should make this a bit nicer just so we can. All right, CLA, again, labeled. So we want to loop back here at the end, so I'm going to give it a label. So we're going to loop, and then what we want to do, we have an empty accumulator now. So we want to add the multiplicand, which we gave this value MLP here, and that's at 9FF. So we're going to add that to the accumulator. We're going to use that ISZ instruction we talked about earlier. So increment and skip if 0. So we increment the counter, and if it's 0, we skip. So we skip this instruction if the counter is 0. What we're going to put here is like an exit from the loop. So BUN to LOP. So what this means is if it's 0, it'll skip this. So it won't do that. And what it will do instead is it will then, excuse me, BUN to an indirect one. And then, oh, right, that's why it said that, just because we had a return address stored here. Oops, are allowed. For the places, the multiplicand, the multiplier. It's all to this past. Oh, okay. I understand what they were doing now. Okay. I'm just gonna restart this. So org, we set our origin, hex 9FF. That just indicates that it's a hexadecimal number. So the origin, the next line will be at 9FFF. And we were told that 9FFF contains the multiplicand, which we're going to call MLP. So this is just a label. We can just give it the value 000 here, just because it's a generic thing here. So this is 9FF. Next, and as we said before, we want our subroutine to start at address A00, and we're going to call this subroutine MUL. I forgot to read that earlier. Read the whole question, it helps. So we have MUL, and that's our label for where the subroutine is stored. Oops. And it's just going to be an address. Well, it's just a label for this point in memory. All right, now, so we were told already that we have the multiplier and the accumulator. So we're going to use our multiplier as our loop. Multiplier, we do it 4 times, right? So again, complement the accumulator, increment the accumulator, because now we have -4 the accumulator. And then STA out of a variable, we're going to call it CTR. Clear the accumulator. I'll write comments here after, and then we can go through this. Next, we're going to make another label called loop. We want to add the multiplicand at 9FF. Excuse me. So that's up here. We want to add that, and then we want to do that 4 times. So we do our ISZ CTR. So we increment the counter. So right now the counter is at -4. If we increment it once, it will be -3, which means we want to do it again. So we can just branch to our loop again, and that will go up here. And every time it does that, it will keep incrementing the counter until the counter equals 0. And then when the counter equals 0, it will skip this BUN. And then we can just say BUN MULI. And that's because we're saying that when you call to a subroutine, we store. Yeah, I should have actually gone over BSA. That would have made it a lot more clear. Let's do that really quick. It's a bit out of order today. Sorry about that, but we're gonna go up to here. The BSA instruction is very powerful. It allows you to have complex decision structures in your programs. So how it works. If you call, for example, we're going to use BSA 135 here. So when you call BSA 135, what happens is it first loads the program counter into the memory unit of the instruction in the address register. So if you have, oops, this is not a notepad. You're welcome.
And good luck.
Thank you. All right. Bye now. Let's go over BSA really quick. So BSA 135. So what's going to happen? Yeah.
Okay, so that one is
Yes,
I'll
send it on all the Discord. Yeah, I'll do that. I sent it on the chat, but yeah, I'll do that.
So
All right, see you then.
BSA 135, what's going to happen is it will store that value. It'll store the program counter. So remember, when you're executing an instruction at 20, the program counter, because it's already been incremented, contains 21. So that's the address of the next instruction. Can I give them a second there? So we're going to go to BSA. What happens is we store the value of the program counter at the address that's been specified. So BSA 135, what's going to happen is M135, that's where we're going to store the return address, the address of the next instruction, right? Now it contains 21. And then what happens is it will actually load into the program counter the next instruction. So it'll load this 135 but incremented. So it'll load 136 into the program counter. So then it will start executing the subroutine. And then when you reach the end of your subroutine, what you have to do is you have to put this in manually. You have to say 1 BUN and then wherever that start of your subroutine was, right? Or the address before the start. So what will happen is it will go, it won't branch to address 135. It'll branch to the address stored at 135, right? So it'll go here, it'll go to 135, it's like BUNM1, like that. So it won't branch to 135, it'll branch to the address stored at 135, which is 21. So it'll go back to 21. So now, if we look here, we can go back to our other instruction, which explains why it's kind of looks like the way it is. So MLP, that's kind of, that's our label for this. That's our label. So in this case, it's kind of like saying 135. That's our label for how we're going to call it with, or sorry, MUL, not MLP. MLP is just a variable that we get to store at. So we are calling MUL, and the actual address that MUL is a label for is where the return address will be stored. So then you execute your subroutine, and then when you're finished, you can then do an indirect branch, an unconditional indirect branch to MUL. So remember, it will have saved a return address here, then it started executing the instructions after it. Then what happens is it will branch indirectly to whatever address is stored here. So if we were at, let's say we were currently executing if program counter currently equaled 21. So the next instruction to be executed was 21. And we had a DSA MUL. What happens is it would save 21 in address MUL and then branch to the address MUL +1 and execute this. And then when you're done that, then you can do your BUN MULI. So whatever address we saved here, in this case, it would have been 21. Or it would have been, sorry. Or yeah, it would have been 21. So we're not going to branch back to this address because then we would just keep doing our loop over and over again. Instead, what will happen is it won't branch to MUL, it'll branch to the address stored at MUL, which is 21. And then it will continue back off after where you called your subroutine from. Now I know it is a strange concept. Why are MLP and why are MLP and MUP 0000? So it's 0 in this case. This really could be anything. This is a MLP, that's the multiplicand, and then MUL, that's the subroutine. So we just gave it the placeholder values of 0000, just so that, because really it can be anything depending on the context. So here your return address would be stored, and here would be the value that you're multiplying would go, which would be the multiplicand. That's what MLP stands for here. So if anyone has any questions, please ask, because I know it is a bit confusing. Or if you understand, then that's great. Anyone? You actually understand it? No? Okay, so yeah. So if you're doing, you would have 6 stored in MLP. Remember, we were told here that the other value was stored, where's the question? Was stored in the accumulator. And then what happens is we turn that value into a counter. So we add this value to itself, the counter number of times, which in this case is 4. Because remember, we turned 4 into a counter because it's in the accumulator. So we complement it and add 1. That turns it into the value -4. And then we clear the accumulator. So, and then we stored that counter at this other location in memory, right? Oh yeah, we should have had another place in memory, CTR, and then we'll just give it another placeholder value. All right. So we store a counter here. Now the accumulator is 0. We add the number that we want to multiply. In this case, this would be 6 for us, right? We add it to 0, that's 6. We increment the counter and check if it's 0. If the counter is 0, we skip this next instruction. But since it's not 0, we do this next instruction. So BUNLOP, which goes back up here. And then we do it again. So we do it 4 times because our counter was set to -4. And then once that counter is 0, it's going to skip this. So it won't perform this, and then it will enter the return phase where, remember, we saved our return address up here. So we don't branch to MUL, we branch to the address saved at MUL. So does that make more sense? Okay, awesome. Any other questions in the room? This whole programming thing is a bit confusing. Yes, that's true. Welcome to assembly. All right. So we, do you guys want to go over part B of the question? It's basically just using that subroutine now, expanding, you use it to compute a dot product, which is crazy fun, as you can imagine. Or if you want, you can go look at the solution. You guys want me to go over it? Or do you have places to be? I know I am over time. Yeah. All right then. Yeah, I'll upload the solution of this exam. Yeah, although if everyone leaves, I'm probably not gonna go over this, although I did do this question last year and I can send a link to when I solved it last year as well. Okay. Cool then. All right then. So what do you guys want? Are people staying or no?
Yeah.
Pardon me? You're leaving? Is everyone leaving? All right then. So yeah, we'll call that for today then. All right. Thank you so much for coming, guys, and we will upload all that stuff. Sorry it was a bit messy. Been a while since I've done some of these questions. And oh yeah, anyone in the Zoom chat? Any questions there?
When I said, oh, it's gonna be recorded. They're like, okay,
Okay.
we're gonna watch the recording.
Awesome.
That's
Fair
really-
time. All right then. All right then. Thanks for coming, everyone. Have a great day.
So thanks, guys. Can get more. Are there any more cookies?
There's one left.